Hello, and thank you for your interest in this session. This is a pre-recorded presentation for our regular paper contribution to the 2021 American Control Conference. My name is Mohammed Fayjoun, and I would like to thank my co-authors, Professor Costas Sakalis and Professor Greg Rapp of the Fulton Schools of Engineering at Arizona State University. I'd also like to thank the conference organizers for the opportunity to present a spectral decomposition identification algorithm for structured state space models, with an emphasis on estimating semi-physical models of social cognitive theory. For a quick overview, we'll start with the main problem in this paper, which is how to develop a systematic approach to estimating gray box models of a linear structure from input-output data, all in the absence of prior knowledge that is often needed for solver initialization. We know that gray box models usually emerge from the simplified dynamic description of physical, semi-physical, and network systems. More particularly, we were motivated by the need for estimating and validating a semi-physical social cognitive theory model using published participant data from the Just Walk behavioral experiment. In this work, input-output data of Just Walk were extracted directly from the cited references with high accuracy using a specialized software tool. So the first challenge we have is that the typical gray box identification problem poses as a non-convex, nonlinear least squares minimization problem. Hence, the selection of good initial guesses is crucial for success. So this is the convexity problem. The second challenge is identifiability, which concerns the uniqueness of the model. The model structure and/or experiment design can render the concerned model unidentifiable. So how do you approach these challenges? In this paper, like recent contributions in this domain, we relied on first estimating a total discrete time model, say a subspace model, and then utilize the identified system characteristics in the estimation of the structured continuous time one. And now on to the main formulation of the proposed algorithm. We mentioned earlier that one may start with a black box model, and in this case, a subspace model such as N4-SID, which is an acronym for Numerical Algorithms for State Space Subspace System Identification. Here, the initially estimated subspace model in discrete time satisfies the system of linear equations expressed by 1. One key observation to make here is that an identified subspace model is unique up to a similarity transformation. Note the 3 typographical corrections to the paper written in red. Not to worry, these are the only corrections that are made in this presentation. For this method, 2 assumptions will follow throughout the presentation. However, we know that there may be cases when one or both assumptions are violated while the method remains effective. The first assumption is that the discrete time state transition matrix has n distinct eigenvalues. This is one way to guarantee that AD is diagonalizable. The second assumption is that we assume zero-order hold intersample behavior during the identification experiment. From the known exact discretization of zero-order hold sampling, this second assumption produces the result for the integral in 2b. With equations 2a and 2b, a spectral decomposition of AD gives rise to equations 3a and 3b in bold that are key to the proposed formulation. Now, the established decomposition eventually leads to the shown augmented quadratic program. More on the intermediate steps leading to this formulation can be found in the paper. I apologize for this busy slide, but we only know 3 things here. First, if the nonlinear structure implies any relation between an entry of A and an entry of B, then the augmented structure matrix P is provided by the user. The form of the given matrix in this case will indeed not be block diagonal as shown. The other note here is that the vector phi is system invariant, and hence does not depend on the applied similarity transformation during the search. Lastly, with this formulation laid out, the paper carries on and delivers sufficient conditions for the existence and uniqueness of the SD model, as well as some conclusions on identifiability. An analytic solution to this formulation is also given in the paper. Now, to formulate a loss function, there may be more than one way to utilize a spectral decomposition formulation. In the paper, we have chosen to feature a relaxed, or rather an approximate error function with an ability to capture the SD model exactly in a subspace of feasible similarity transformations from a structural standpoint. This is, of course, when assuming zero-order hold. We refer to this function in the paper as standard because of its quasi-linear form. However, for a more exact error description, if needed, our SD formulation can be used in the classic PEM loss function. Of course, this will come at the cost of adding more computation in each iteration. Now to the final piece of our proposed framework. One may ask the question, what if the identified lambda d is not positive semi-definite? Of course, the question implies that one or more of the identified eigenvalues of the discrete time model have negative real parts in the z-plane. Consequently, the model is not physically realizable and cannot be transformed into a continuous time image without increasing the order. The matrix logarithm is undefined for AD with eigenvalues of negative real parts. So the approach taken in this work is to obtain optimal eigenvalue constrained subspace models by using linear matrix inequalities, or LMI in short, to formulate constraints that place eigenvalues in the desired LMI regions in the z-plane, or the unit circle. For example, here we can see that many of the commonly desired characteristics, such as stability and physical realizability, can be described by convex sets or regions in the z-plane. Further, it is also known that the intersection of two LMI regions is an LMI region, which facilitates the enforcement of multiple model criteria simultaneously when solving the convex semi-definite program developed in Miller and DeCalifon in 2012. We invite you to review our paper for more details on this formulation and relevant references. Finally, with all formulations and formalities out of the way, it is now time to illustrate the effectiveness of our proposed method with a relevant numerical example featuring a physical system. In this example, we feature a DC motor system described by the displayed structure state space model, in which the input is voltage and the outputs are angular position and angular velocity. Using the structure state space model, the analytic SD solution, again obtained with no iteration, can be calculated after constructing the structure pair P and D as shown. Input-output data can be retrieved by loading the example ID Demo 7 in MATLAB. In this figure, we show the simulated response comparison for both models, the initially estimated deterministic subspace model in blue and the SD identified model obtained analytically in red. Note that in the applied inputs, which are not shown, a zero-order whole sampling policy was applied in this example as excitations had taken the form of a pseudo-random binary sequence. Note the remarkable improvement made by benefiting from structural information known a priori. Now let's pivot into the final part of this contribution and present a further simplified model of social cognitive theory. This fluid analogy model attempts to explain behavior change by capturing the dynamics between the individual's behavior outcomes and behavior, as well as the individual's self-efficacy and behavior. Hence, we refer to this model as an operant conditioning self-efficacy model, or OCSE in short. Manipulated inputs include goals, expected reward points, and actual granted points. External disturbances describe some of the most influential contextual factors impacting the individual behavior change, such as predicted busyness, predicted stress, or whether the day is a weekday or lies in a weekend. With a few limitations to be outlined later, also in the paper, our focus will be on estimating and validating this model structure using real experimental data. Now, for model estimation, we estimated 3 separate models for both featured participants in the paper. The first model in blue is a classic unconstrained subspace model. The second model in red is an eigenvalue constrained subspace model in which eigenvalues were made to lie within the intersection of all LMI regions discussed earlier. The third model in gold is an OCSE social cognitive theory model, which represents our gray box structure, estimated by initializing PEM using an SD identified model. The shown plot shows how all 3 models fit the estimation data. For quantifying the goodness of fit, we consider the normalized root mean squared error metric. As expected, the more constraints are added, whether concerning the system poles or structure, the less fit to the estimation data we get. However, as we will see in the next slide, fits to validation data will give an entirely different story. See here, with validation data, it is quite clear that the more prior knowledge incorporated into our model, the more predictive our model becomes, with the OCSE semi-physical structure outperforming both black box models. Note how bad the unconstrained subspace model performed over validation data. This is indeed a clear sign of overfitting or overparameterization. More on validation. In addition to the goodness of fit, one may also verify results from residual analysis, which were not provided in the paper for brevity. Here, from the display plots using 99% confidence intervals, both the whiteness and independence tests conclude that the residuals of the estimated OCSC models are not autocorrelated nor cross-correlated with past inputs. Hence, using these classical tools, the identified model has not been falsified by the data. To conclude, we summarize our contribution in that we have delivered an identification framework for estimating gray box models. Further, a lower complexity SCT model was introduced, estimated, and preliminarily validated in the context of JustWalk. Some of the limitations in this work can be summarized in 3 points. First, as the case with all existing algorithms known to authors, the SD formulation remains non-convex when P is less than N. Second, the formulation applies only to systems in which the state transition matrix AD is diagonalizable. Third, the lack of measurements for self-efficacy and behavioral outcomes in JustWalk created a barrier from validating the SCT model most formally. Please refer to the paper for an additional example highlighting partial identifiability and its consequences on formally validating any of the published SCT models thus far. Finally, we highlight some of the potential future directions in this domain. First, one may explore extensions to the existing formulation for enforcing stability constraints. Additionally, some preliminary theoretical analysis for quadratic structures resulting in a form that is consistent with a quadratically constrained quadratic program in 6 may be pursued. Thank you for listening. Happy to answer questions in the live session.